So, any time domain signal may look like this. It may be a simple sine wave, or it may have some, okay. It may be periodic, or it may not be periodic, right. So, these are time domain signals. Okay, this is a time and this may represent the voltage. Okay. So, maybe we are interested in knowing what are the frequency components. Okay, what are the frequency components in this particular signal? Remember that there is a very important result, okay, due to Fourier, which talks about how a periodic waveform like this, okay, suppose the frequency of this waveform is 1 kilohertz, okay. So, this is 1 millisecond, 2 milliseconds, etc. Okay. So, this is a periodic 1 kilohertz waveform. Okay. The period is 1 millisecond. Okay. So, according to Fourier, you can take this waveform and split it into a number of components. Okay. One is a pure sine of 1 kilohertz, then it could be another pure sine of a multiple of, so 2 kilohertz, 3 kilohertz, 4 kilohertz, etc. So, you will take this and decompose into a number of sine waves, okay, sine or cosine, okay, both sine and cosine, combination of sine and cosine waves. This is the the base frequency. Okay, if this is a 1 kilohertz waveform, okay, then this will also be 1 kilohertz. So, this is the base frequency, and these are sometimes called as the harmonics. Okay, these are the harmonics. So, any periodic waveform, in fact, if you take a square wave, okay, let us say this is a 1 kilohertz square wave, we will be able to split it into a sine, okay, and a number of harmonics. Okay. So, this is a sine wave of 1 kilohertz, the basic frequency, and a number of harmonics. Okay. Similarly, if we have a triangular waveform, of 1 kilohertz frequency, this also can be split into a sinusoidal plus several harmonics. Okay. So, FFT analysis allows you to take any periodic waveform which is somewhat arbitrary. Okay. It need not even be a triangular or a square or something like it could be quite arbitrary like this, but you can split it nicely into a sum of sine and cosine waveforms. Okay. And that is a property that is useful in analog testing. Okay. So, basically we have replaced with a sum of various, this is a pure sine, pure sine, pure sine, maybe twice the frequency, 3 times the frequency, etc. And this may be my maybe analog circuit. Usually we don't need to go beyond maybe 3 or 4 of these, because the amplitude of these harmonics will decrease very sharply. See, this will be a fairly strong component, but the others will sort of deteriorate very quickly. Okay. So, I will show you this with the example, right, of maybe a square waveform or something like that. Okay. So, I was telling you about Fourier transforms, right. So, let me show you. So, you can go to this Wolfram math world, okay, and search for Fourier approximation of a square wave. Okay. So, this black waveform is a square wave. Okay. The period is capital L. Okay. You could have used capital T, which is very common, but they have used capital L. Okay. So, the period of this black square waveform is capital T. Now, what you can do is, you can imagine a sine waveform of the same frequency. The red curve is a sine waveform of the same frequency. Okay. Then you have to imagine a sine waveform of 3 times this frequency. Okay. So, 3 times means it will have in this same period you can accommodate 3 sine waves. Then another one with 5, another sine wave with 5 of these sinusoidal waveforms and so on, only that their amplitudes will be smaller. Okay. So, the Fourier series decomposition of a square waveform is what is shown here, right. It is 4 by pi of 1 by n sine n pi x by capital L or T, whichever you want to call. Okay. And only the odd harmonics are present, okay, 1, 3, 5. So, in this particular example of a square waveform, only odd harmonics are present. Okay. In the same way, you may want to check out a triangular waveform. Okay. Again, Wolfram has the answer, right. So, you can see that if this black waveform represents a triangular waveform, then the red one represents the 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 main base waveform. Okay. It is a sinusoidal waveform. To that you can add several harmonics to get back the triangular waveform. Okay. So, this is the construction of the triangular waveform, okay, using so, let me illustrate the, I think so, this also explains the same thing. The blue waveform can be constructed as the sum of a number of okay. So, let me try to illustrate this. So, let us create the period to be 1 millisecond. Okay. Let us assume the period to be 1 millisecond, and let us take t to be a time sample, right, linearly sampled from let us say 0 to let us say 5 times t. That means 5 waveforms. Okay. And then f is nothing but 1 over t, the frequency. Then omega is 2 pi f, right, and let us say v is 1 volt peak to peak multiplied by sine of omega t. Okay. Let me plot this and show you. Okay. So, we will just get a waveform, sine waveform, nothing else will happen. Okay. So, if you run this guy, so I have plotted a simple sine waveform. I start from t equal to 0 and went up to 5 times t was 1 millisecond. So, I went up to 5 milliseconds. So, there are 5 waveforms 1, 2, 3, 4, 5. The peak value is 1 volt, okay, and the frequency is adjusted to have a period of 1 millisecond, right. Now, let me take a harmonic. Okay. So, in this example, instead of 1, let me make it 4 by pi. Okay. Because that is what that Wolfram website says, 4 by pi. V1 is 4 by 3 pi multiplied by sine of 3 omega t. You understand? So, and then we plot t and V1. Okay. So, we will do both. So, you can see that we have plotted the this is the 3 omega t. Okay, this is 3 omega t. Let us increase the number of points. So, we can increase it to maybe 500 points. That will look better, the waveforms will look better. Okay. You can see this is the 4 by 3 pi into sine of 3 omega t. Then we will plot t v plus v1, okay, the original and the harmonic. Then we will see how that looks like. Okay. So, you can see that the original plus the harmonic is beginning to look a little bit like square wave, right. Let us add the third harmonic, or I am sorry, the fifth harmonic. And we can add, we need not display these things, this is not so important. E1 plus V2. Okay. So, if you run this now, you will see it is going to look a little bit more like square wave. Okay. So, if I add more and more of this, okay, this is the fifth, this is the third harmonic, this is the fifth harmonic, then I can add the seventh, ninth, etc., all the odd harmonics. Only thing is their the amplitude will keep reducing. See, the amplitude of the main harmonic is 4 by pi, the other one is 4 by 3 pi, 4 by 5 pi, 4 by 7 pi. So, it will keep reducing, okay, and the resulting waveform will begin to look more and more like a square waveform. So, here what I have done is I have gone the reverse way. I have shown you how you can add a number of sine waveforms to build something that looks like a square waveforms. If I am willing to take infinite number of these sinusoidals, third, fifth, maybe if I am willing to go to 101, 103, etc., you will possibly, you can imagine that it will be almost like a square wave and it will have the same frequency. See, this is a period is again the same thing, right? Its period is also 5 milliseconds. Okay. So, I have synthesized the square waveform from sinusoidal waveforms. Okay. So, according to Fourier's series analysis, you can do the same thing for any arbitrary waveform which is a periodic waveform, and the series tells you how to do that. Okay. It tells you, by the way, it should be a combination of sine and cosine. You cannot always have only sine components. In the case of the square waveform, it was a special case, all the components were pure sines, but in some cases we may have a combination of sine and cosine. Okay. And the Fourier series analysis tells you how to estimate the amplitudes of the harmonics, which could be either sine or cosine. Okay. So, that is the analysis part. There is synthesis and analysis. In synthesis, I start from sine and cosine waveforms, I add them up to get the desired waveform. In the analysis, we do the other way around. We start with an arbitrary periodic waveform and we decompose it into a number of sine and cosine harmonics. Okay. Why is this important? Okay. What is the reason why this is important? Right. Sometimes when we want to look at a waveform that an analog circuit is generating, more than the time domain waveform, okay, the time domain waveform can be viewed, right, but if you want to draw some conclusions about that waveform, maybe it is easier to perform a Fourier series analysis. Okay. and see what is the power level or what is the amplitude, right, of each of the harmonics. Okay. You will find that there will be the main component whose frequency is f, where f is the frequency of the original periodic waveform. That will possibly have a strong component, right, and the harmonics will have a smaller role to play, their amplitudes will be smaller, right. So, that is what we are also seeing here. We are seeing 4 by pi. Okay, this is the sort of frequency of the main base waveform. This is 1/3, this is 1/5, 1/7, 1/9, etc. So, it will sort of, the amplitudes will be decreasing over a period of time. Okay, or as the and I should not say over a period of time, I should say the amplitudes will decrease when I increase the the harmonic number. Okay, is that clear? So, in the analog circuit, if it generates, let us say it was intended for generation of a pure sine, okay, but maybe because of some non-linearities in the circuit or some defects in the circuit, it may be having some harmonics in the output and resulting in some distortion. Fourier analysis can help us in understanding what are the components of the harmonics, right, and we may be even able to filter out those components and things like that. Okay. So, from a test perspective, you may be interested in measuring the nonlinearity of that circuit. Okay, how much harmonic it is generating and things like that. So, that is the reason why it is important to do a Fourier analysis, right, and there are equipment, there is measuring equipment which can do this for you, okay, which can we do not have to sit and do the Fourier analysis by hand. Of course, you can use a tool like Octave or by the way, Octave is nothing but a very software very similar to MATLAB. Whatever I have done here, you can also do it in MATLAB. The same commands will work. So, Octave is free. Okay. I was using an online Octave compiler. You can also use something that you have downloaded, right. So, this is an Octave online compiler. Okay, I may have forgotten to mention that. So, to do whatever I have just done, use any one of the Octave online compilers, and this is the editor where you can write down all the commands, okay, and then you can say run, and it will you can also save whatever you have written. So, FFT analysis is useful in analog testing, right, if there are parametric faults such as the resistance may have some variation, right. We can never get exact resistance, we can never get exact capacitance, etc. So, there may be, and these things also vary with temperature, etc., right. I mean, the resistance varies with temperature, right. So, because of these parametric faults, there may be some variation in the frequency. Okay. So, this will result in small changes in the output which are not easy to perceive by looking at the waveform. But if you perform the FFT analysis, then it will clearly show you where the what are the frequencies which are present in the output. Okay. What is the main frequency, what are the harmonics, all that will be clearly shown. So, distortion, for example, will be clearly visible in the Fourier analysis. Okay. Okay, let us continue. I found a nice website where this Fourier analysis can be understood nicely, right. So, this is the website falstart.com Fourier, right. So, I hope you can see what I have. So, there are several waveforms that you can bring up. You can bring up a sine waveform, cosine waveform, triangular waveform, sawtooth, square, right, noise waveform, right. So, if I take a sine waveform, you can see that the only component in this sine waveform is one sine. Okay. So, if I drag this, I can adjust the amplitude of that sine waveform. Okay. It is also showing you the frequency, etc. Okay. There is no cosine here. Right. Similarly, I can take a cosine waveform and I can adjust the amplitude. Okay. There are also the second harmonic, third harmonic, etc. Right now, there is no all the other harmonics are 0 except the first harmonic. Okay. So, in the same way, if you take the sine waveform, only the main base waveform is there, the others are not there. So, if I drag this guy, so what has happened is I have added the sine plus in this example maybe half. Okay. So, there is sine omega t plus half of sine 2 omega t. Okay. Suppose I take 1/3 of sine 3 omega t. So, this is sine omega t, this is approximately 1/3 I can see, right. See, if this value is 0.749 is RMS value, whereas here it is I am sorry, the it is 1 sin x, you can see 1 sin x, right. So, this is approximately 0.33. Okay. I can adjust this to be 0.33. When I add them, it looks more or less like the square waveform, right. Then I can add 1/5, that is 0.2 of the fifth harmonic. Okay. And then 1/7 of the seventh harmonic. Okay. So, the more I add, you can see that it is beginning to look more and more like a square waveform. Okay. The same thing is illustrated here. Okay. So, this is the sine waveform. Okay. The original waveform is a square waveform. If I want to see it as a sum of all these guys, I can go and if I put it here, it shows you the sine waveform, right. So, this is 1.27324 sin x, this is 0.4244 sin 3x. Okay. See, how did it come to 1.27324? I believe it is 4 by pi. Okay. So, this is 4 by 3 pi, 4 by 5 pi and so on. Okay. So, when I add these guys together, I will get this square waveform. If you want, you can experiment by adding a little bit more of this. Okay, then it does not look so much like a square waveform. Okay, so, you have to do exactly whatever they have provided. Okay, so this is a very beautiful online tool which shows how you can compose a square waveform by combining sines and cosines. In this case, there are no cosines, okay, but you are welcome to add some cosine component. It may not look like a sine waveform. Okay. So, you have to go by whatever is recommended. Okay. So, the theory tells you that to create a square waveform from sines, you have to start with 1.27324 sin x or sin omega t. To that you have to add 0.4244 sin 3 times omega t, 0.25463 sin of 5 omega t, etc., etc. Right. If you add some arbitrary ones like this, okay, it distorts the waveform. It is no more a square waveform. I hope this explained. Okay, so you can also try out rectification, right? Full rectified waveform and so on and so on. I think you can also hear the sound. See, this is a pure sine. Okay, if you take a pure cosine, it may look like this. If you take a triangular waveform and try to listen to it, it looks very different. Okay, if you play a sawtooth, it may sound like this. Okay, so you can even try to combine. You can play with this sinusoids and see how it looks, how it sounds. So, this is an arbitrary waveform that I have created by adding a bunch of sines and cosines. It may not sound very pleasant. Okay. So, you can see to generate good sounding music, you will have to work on this. Okay, it has to have proper harmonics, etc., so that it will sound pleasant. Okay. You can also, I think, modify the number of terms and the frequency. Okay, we can reduce this frequency and try to play it. You can reduce the frequency further and try to play it. So you can experiment with this, right? So what did we learn from this? The fact that if this is output of some analog circuit, right, I can do a Fourier analysis, okay, and it will decompose this guy into the constituent sines and cosines. Okay, and from a test point of view, it helps me to understand, how far it is from the original expected waveform. The original expected may be a pure sine. Okay, this may be the expected waveform. Yeah, this may be the expected waveform, but because of some various non-linearities, etc., I may be getting slightly, see, it's not easy for the eye to recognize the non-linearity here. It looks like a sine only, okay, but you can see that there is some, distortion. Okay, there is a second level harmonic here. Okay, so this is very visible. Okay, this clearly is not a pure sine. There is some third harmonic causing it to look almost like a square waveform. Okay, so we have to. That is what the advantage is, right? So sometimes what you cannot catch in the time domain, you can catch in the frequency domain. Okay. See, when you test digital circuits, it's very easy to check the zeros and ones and conclude that the circuit is behaving differently and reject the circuit. But when you are doing analog circuits, see if the output waveform has a little bit of distortion like this, it's not easy for us to look at the waveform and say that it is not doing what it is supposed to do, etc. But if you can do the Fourier analysis, then it is very easy for you to figure out how much the nonlinearity is and whether it is acceptable, not acceptable, right. So, okay. So, this is a very nice website, fallstar.com. So, please play with it, okay, so that you can understand. All right.